15th of July 1943. Heat shimmers rise from the airstrip at Benina, Libya. Major Theodore Hartmann stands beside a Curtiss P-40 Warhawk, its engine cowling removed. Inside, the cylinders are scored deep, metal ground to ruin. The aircraft has flown less than 20 hours. Hartmann is a maintenance officer with the United States Army Air Forces, and he faces a crisis that threatens to ground the entire North African air campaign. Sand, fine desert grit, invisible in the air, pulled into engine intakes with every flight. It bypasses the standard filters, enters the combustion chambers, and acts like grinding paste between pistons and cylinder walls. Engines that should last 200 hours are failing at 20. Across Libya and Tunisia, fighter squadrons sit idle while mechanics tear down engine after engine, finding the same destruction. Hartmann has watched this pattern for weeks. Now he must solve it, or Allied air superiority over the Mediterranean will collapse. Hartmann is 32 years old, an engineer from Michigan who worked in automotive design before the war. He understands filtration systems, airflow dynamics, and the brutal reality of field conditions. He knows that standard air filters were designed for temperate climates, not for the Sahara. The mesh screens and simple fabric elements cannot capture particles smaller than 50 microns. Desert sand averages 5 to 20 microns. It flows through the filters as if they do not exist. He begins by studying the sand itself. He collects samples from airstrips across the region, examines them under a field microscope, measures particle size distribution. The sand is not uniform. Some grains are coarse, easily trapped. Others are powder-fine, almost like talc. These are the killers. They remain suspended in the air for hours after a sandstorm, drawn into engines during takeoff and landing when airflow is highest and altitude is lowest. Hartmann calculates the volume of air an aircraft engine consumes. A P-40 at full throttle pulls in over 10,000 cubic feet per minute. Even if the air contains just 1 gram of sand per cubic meter, the engine ingests hundreds of grams per hour. Most of it passes through, but even a small percentage that enters the cylinders is enough to cause catastrophic wear. He needs a filtration system that captures 99% of particles down to 5 microns, operates reliably in extreme heat, and can be installed quickly across hundreds of aircraft with limited tools and supplies. The solution comes in 2 stages. First, an oil bath pre-cleaner. Hartmann designs a chamber mounted ahead of the main air intake, where incoming air is forced to make a sharp turn through a pool of engine oil. Larger particles, unable to follow the airflow around the turn, impact the oil surface and are trapped. The oil acts as both a barrier and a collection medium. It can be drained and replaced easily, removing accumulated sand without disassembling the system. Second, a pleated paper filter element. Hartmann sources industrial filter paper used in American factories, material designed to capture fine particles in manufacturing processes. He designs a pleated configuration that maximizes surface area within a compact space, allowing high airflow with minimal pressure drop. The pleats are sealed into a metal frame that fits into the existing air intake housing. The paper captures particles down to 5 microns with 98% efficiency. Combined with the oil bath pre-cleaner, the system achieves the filtration performance he needs. But designing the system is only the first challenge. Manufacturing and installing it across an entire theater of operations is another. Hartmann has no factory, no production line, no supply chain. He has a maintenance depot at Benina, a handful of skilled machinists, and whatever materials he can scrounge from salvage yards and supply dumps. He organizes a small team. Sergeant Raymond Cole, a sheet metal worker from Pennsylvania, fabricates the oil bath chambers using aluminum salvaged from damaged aircraft. Corporal James Liu, a machinist from California, manufactures the metal frames for the filter elements. Private First Class Anthony Rossi, a mechanic from New York, develops the installation procedure, determining exactly how the new system fits into each aircraft type without requiring major modifications. The filter paper is the bottleneck. Hartmann requests shipments from the United States, but supply chains are stretched thin and priorities lie elsewhere. He searches locally. In Tripoli, he finds a warehouse containing industrial supplies left behind by Italian forces. Among the crates, he discovers rolls of German-made filter paper, intended for industrial air compressors. It is high quality, possibly better than what he requested from home. He requisitions the entire stock. By the 28th of July, the first prototype systems are ready. Hartmann installs them on 3 P-40s and runs test flights. The aircraft operate normally. Engine temperatures remain stable. Airflow is adequate. After 10 hours of flight time, he inspects the filters. The oil bath chambers contain visible sand, drained away from the engine. The paper elements show surface loading but are not clogged. The cylinders, when inspected with a borescope, show no scoring. The system works. Now comes the rapid field retrofit program. Hartmann has hundreds of aircraft to equip and a maintenance force that is already overworked. He cannot pull every aircraft out of service simultaneously. He develops a rolling installation schedule, prioritizing squadrons based on operational tempo and engine condition. Each installation takes 4 hours. He trains crews in groups of 12, teaching them to fabricate, install, and service the new filters. The training is hands-on. Hartmann demonstrates each step, then watches as mechanics perform the work themselves. He emphasizes the importance of proper oil level in the pre-cleaner, correct sealing of the paper element, and regular inspection intervals. He creates illustrated manuals, simple and clear, that can be understood even by mechanics with limited experience. He establishes a supply system for replacement filter elements, ensuring that every airstrip has adequate stock. By mid-August, over 200 aircraft have been retrofitted. The results are immediate and dramatic. Engine life extends from 20 hours to over 200. Squadrons that were grounded return to full operational status. Sortie rates increase. Maintenance crews, no longer consumed by constant engine rebuilds, can focus on other tasks. The air campaign over the Mediterranean intensifies, but the system requires maintenance. The oil bath chambers must be drained every 10 flight hours. The paper elements must be inspected and replaced when surface loading reduces airflow. Hartmann establishes a rigorous service schedule and trains crew chiefs to enforce it. He knows that a filtration system is only effective if it is properly maintained. Neglect will lead to clogged filters, reduced airflow, and engine damage just as severe as sand infiltration. In September, a sandstorm strikes Benina. Visibility drops to 0. Wind gusts reach 60 miles per hour. Sand fills the air like fog. When the storm passes, Hartmann inspects the aircraft. The oil bath chambers are full of sand, but the paper elements are clean. The engines, when tested, run smoothly. The system has protected them even under the worst conditions. He drains the oil bath chambers, replaces the oil, and the aircraft are ready to fly. The success of the filtration system spreads. Other theaters request information. Maintenance officers in India, facing similar problems with monsoon dust, adopt Hartmann's design. Engineers in the Pacific, dealing with volcanic ash, modify the system for their conditions. The two-stage filtration concept becomes standard across multiple environments. What began as a field expedient in North Africa evolves into a permanent solution. Hartmann documents everything. He writes technical reports detailing the design, materials, installation procedures, and maintenance requirements. He includes performance data, failure analysis, and lessons learned. He submits the reports to Army Air Forces headquarters, where they are compiled into technical orders and distributed throughout the service. His work influences post-war aircraft design, leading to improved filtration systems in both military and civilian aviation. By the end of 1943, engine attrition due to sand infiltration has dropped by 95% in the Mediterranean theater. Aircraft availability rates reach the highest levels of the campaign. Allied air superiority is maintained, supporting ground operations in Sicily and Italy. Hartmann's filtration system is a critical enabler, invisible to most but essential to success. In December, Hartmann is reassigned to the United States to work on advanced aircraft development. Before he leaves, he conducts a final inspection tour of the airfields he has served. At each stop, he meets with maintenance crews, reviews their procedures, and ensures that the filtration systems are being properly maintained. He sees aircraft with over 300 hours on their engines, still running strong. He sees mechanics who understand the importance of the work they do, who take pride in keeping their aircraft flying. At Benina, he stands again beside a P-40, its engine cowling removed. This time the cylinders are clean, the pistons smooth. The aircraft has flown 240 hours. The filter system, mounted just ahead of the intake, is stained with oil and dust but intact. Hartmann closes the cowling and walks away. The war continues. Aircraft fly, engines run, and sand still fills the air. But now there is a barrier, a system that captures the invisible particles before they can destroy. Hartmann's engineering has turned a crisis into a solved problem, proving that sometimes the smallest particles determine the largest battles. His filtration breakthrough sustains Allied air operations across the Mediterranean, and his methods endure long after the war ends. A legacy written not in headlines but in the quiet reliability of engines that keep running.